Okay. Hello, everyone. Today, we're going to present a talk that we've prepared for DEF CON. Unfortunately, due to some technical issues, we couldn't present. So as we promised during DEF CON, we are now recording everything. So hope you enjoyed. The talk is called Prompt Scan Exploit, AI's Journey Through 0 Days and 1,000 Bugs. And we are basically going to talk about what we have been working during the last couple of months. First of all, we would like to present ourselves. We are Joel Noguera and Diego Jurado. We are both security researchers at Xbow. And for those meeting us for the first time, we have been in the bug bounty field for a long time, attending multiple hacking events. And we have been full-time pen testers for well-known company as well. So before we jump into the good stuff, we would like to do a quick recap of our progress during the last year. Last year in DEF CON, we show some of the results that we were getting once we started with this. So we'd like to see how things have evolved since then. Last year, we showed that we went from AI struggling to find any vulnerabilities to building a system that was able to solve 75% of Porsche triple labs, 72% of pentester lab exercises, and 85% of what we call no benchmarks. Those benchmarks are basically CTFs that were created by ourselves, and that they are not part of any training dataset. So basically, we were using those to verify that things were working as expected. If you remember, we also walked through some cool examples, like an authentication bypass through Python libraries, some reflected and blind XSS, and also some remote code executions. We were proving basically that AI was able to help us to hack smarter and faster. And of course, most of these were CTF-like challenges. So that means that they were developed they were deployed in controlled environments with synthetic setups, and there were not any real data or edge cases. So it was working fine, and the results were really impressive, but it was not what we are expecting in real life. So now we want to show you where we are. Yeah, so let's go and see where today. Right now, our AI is ranked top 1 in the US during 2025 and top 2 worldwide during the last 30 days. That's all in Hackerone. And during the last few months, we were able to find and report 1,600 vulnerabilities and get more than 150K in bug bounties. If you see some of the examples that we have below, you can see that there are some quite examples that we have been sharing already in our blog post. We can see some cool examples like the Salesforce XSS, the Akamai XXE, or even the Palo Alto Network XSS. It was surprising for us that all of these 0 days were sitting there for years, and it was the AI, the one who found it, actually. I want to say that all of these findings were discovered in bug bounty programs. So it's really impressive from the bug bounty perspective that we went from solving CTF puzzles into finding stuff like SSRF through graphical mutations, post-message-based XSS, even remote code executions in WebSockets. Usually those kind of things are findings that require some manual work because they are complex to detect. And in this case, it was the AI, the one that found it without any human interaction.
Oh, sorry, I was muted. Okay, so now that we have more context about where we were last year and where we are now, we also wanted to talk about the things that changed during the last year. So the objective of this talk is to show you everything we have learned, the things we have changed and improved in order to achieve this goal. And if you leave this talk, hopefully you are going to leave with some key learnings about how to apply AI in your daily workflow and how to involve AI in order to improve the type of vulnerabilities you look every day. So as Diego said, at the very beginning, we started with nothing. Then we moved to CTF. Later, we moved to custom benchmarks that weren't part of any training data, but we knew that we need to do something else. So at the very end of 2024, the beginning of 2025, we decided to go and start hunting 0 days and CVEs in open source projects in particular. After that, we moved to the bug bounty field. But before talking about that, let's dig a little bit deeper into this step 3. So as I said, we wanted to leave CTF behind, move to more complex applications with different complexities, different sizes, more real world bugs. So we decided to start making use of Docker Hub repository. If you are familiar with that, Docker Hub is a repository with more than 25 million apps. I think there are more than 3 million web apps in that repository. And the interesting part is that all of them are Docker. So they supposedly they are easier to deploy. And at least is that what we thought at that moment. And we should be able to find quite a huge variety of applications and complexities there. So during this process, it was super interesting also to know that we could extract the Docker content and make that source code available for the agents. So we could also compare black box versus white box approach. And we end up finding more than 170 vulnerabilities, more than 22 CVEs, and we also have some more 150 CVEs pending to be fixed. It's worth also mentioning that we have a backlog of more than 600 vulnerabilities that we have identified, but it results that the process of manually reporting those vulnerabilities to the application vendors, it's quite complex and slow. So we have a lot of work to do yet. So even though we reported all these things and we find quite interesting vulnerabilities, there was one issue with this approach, and is that we didn't see much engagement from the application owners. And we not only want to find a variety of impactful bugs for the community, we also wanted to help the vendors to fix those vulnerabilities. Sadly, this lack of engagement was kind of a dead end for us. So that's why we decided later to move to the bug bounty space. But we did quite a lot of interesting stuff here. At the very beginning, as I mentioned, we thought that deploying Dockers was an easy task. And one may think that those Dockers are kind of ready to be deployed. However, we discovered that that's not the case. Most of them are missing Docker compose files. Others are missing configuration, environment variables. You even need to turn on the application and create and go through a setup wizard in order to make it work. So one of our team members end up even building an LLM power agent that will start spinning up these Dockers, looking at the errors in the console, generating dynamically all the compose files, environment files, and everything we was missing in order to properly set up the Dockers. All that effort and attempts were great. However, we decided to move on from this approach due to the things we were mentioning. So these are some of the examples of the vulnerabilities we were able to report. We can see an XXE in Geoserver, which is a widely application used on the internet. We also found an RCE in Apache HugeGraph, another RCE in PuppyGraph. We also found path traversal vulnerabilities in PDF generators, even an authentication bypass in Scold by just appending a semicolon in the URL that would allow us to not only access the admin API, but also to read files from the file system. We also found an IDOR in Redmine that would allow us to, in an authenticated way, access to all the private projects of any Redmine instance. And we also found some variety of cross-site scripting, some reflected, other were stored. But probably the most interesting one, at least for me here, is the Apache Tomcat XSS. In this case, this XSS was the typical one that we can find on the example projects that come with this server. And a few months later, when we were doing the bug bounty thing, we attempt to report all these vulnerabilities. For example, if you take a look to the Apache Tomcat one, you're going to see we have almost 30 reports in Hackerone, and almost all of them were part of BDP programs. And this was quite interesting because we start noticing a behavior of people that maybe already farming this type of vulnerabilities, but only reporting them to bug bounty programs and just leaving the BDPs behind. So it was super interesting. And if you take a look to the rest of the vulnerabilities, we didn't got max success reporting them in the bug bounty field. So apart from that, I would really like you to show you a demo. The trace we are going to see now, it's pretty simple compared with the things we are doing right now and the example that Diego is going to show later. But it's super interesting because we can observe how LLMs are really powerful into finding new CVEs, and we are going to see how they can use previous knowledge that they have on their data set in order to identify similar vulnerabilities in newer versions. So this vulnerability we are going to see, as I mentioned, is the XXE for Geoserver. We are going to see that the agent starts interacting with the application in order to locate where the application is being hosted. Once located and the DOM is identified, the location of the application is identified, the agent is going to remember that this application, the Geoserver, was previously known to have SSRF vulnerabilities previously, more particular in some of the services that they are exposing on their API. So based on that, it's going to create a POC in order to try to re-exploit that vulnerability in this newer version. It's going to try to exploit that vulnerability, and it will end up discovering that it gets some errors, as we can see here, like missing an invalid request map size, or that other parameters are missing or not presented as expected. So the agent is going to try to adapt to this situation in order to provide all the required information for this service. However, if we pay attention, it seems that the application is not properly configured, and it's saying that there are some missing layers that are not known for the application. Probably the application is just by default spin up and doesn't have any of the required configurations. So the agent will start looking through the application in order to understand the current state of the application. It's going to list the capabilities. It's going to try to access the admin panel, since it's going to try to list the workspace, and it will get the 401. It's going to also try default passwords, as any pen tester would do while interacting with this type of applications. But after that, since none of those attempts are working, it's going to go back to testing, and it's going to attempt to modify the payload and start interacting with different services from the application. After a few trial and errors and trying different attempts, we are going to see that we'll end up building a final POC that is going to finally exploit the XXE for this application. So in this case, it's going to create the payload, and it's going to use this missing layer configuration error we were seeing in order to embed the content of the file we want to exfiltrate and return it in that error message. So later we can see that the flag is returned here, accessing the internal service, confirming the XXE.
Okay, so even after all the success that we were having with the Docker Hub images, and even though we were able to report 100 of 0 days, we still felt that this was not enough. So the worst part of this is that, as Joel was saying, many of these vendors and open source projects were not answering to us, and also those products were not actually exposed to the internet. So we were not having like a lot of impact when we were trying to find this in live environments. So we decided to move completely to bug bounty targets. Basically, we felt that this was the best playground for our AI to start testing and to see if we could improve our working Also, we were moving from white box to black box. So we wanted to see how the AI was able to adapt to this. Also, we were going to start finding and trying to find vulnerabilities that we couldn't find in Docker Hub images because of how they are configured and set up. And also, we wanted to start measuring how good was our performance. So we were going to start competing against a lot of different hackers all over the world, and we were start going to see how the results were for our AI. So when we started this first approach, climbing the leaderboard from Hackerone was not the main goal. We started by improving the product. We started by adding new type of vulnerabilities into our system. But we started to get a lot of different bugs and new findings. In the end, during the last 90 days, we managed to find 132 critical vulnerabilities, more than 300 highs, more than 800 mediums, and 102 lows. And here we have some more stats about HackerOne. You can see here that we have a lot of pending and open reports that still need to be evaluated by the programs. And we can see also that we have a bunch of informative and duplicates, which is something that is also worth to mention. Basically, these informative findings that we were getting were mostly because of 0 days. We know that a lot of programs do not accept 0 days at all. So even though we were finding those and reporting them to the programs, they were basically closing them as informative. Then some of the duplicates that we were having were basically low-hanging fruits from other researchers that were reporting that prior to us. And also something that we wanted to mention is the amount of reports that we had, a non-applicable one. Those basically were closed by ourselves, most of the cases, because we make an error while sending the reports and all that kind of stuff. So as we were mentioning at the beginning, we had a lot of very impactful and really interesting findings that we found during this process in bug bounty programs. So all of the examples that we see here were discovered in bug bounty programs. But we would like to go through one of them, which is a common injection through a server-side JavaScript injection. We think it's a really cool example because it basically reflects everything that we thought about when we started creating this. So we're going to see the AI analyzing the application, getting information about the features, going through all different endpoints, doing some different kind of testing, looking for common injections. Then eventually we'll find out an API, which is a related endpoint, and we'll turn the objective and start testing the API, finding some documentation, then finding a really interesting endpoint, and finally finding the remote code execution. So let's dive into it. I'm gonna share my screen now to show you the example. Okay, give me 1 second. Okay, so here we have the example that I want to show. So here you have the analysis of the comments and what the AI is going to try. First of all, as any pen tester would do, it would start by analyzing the application. It will start by testing with some common injection payloads, because that's the objective that we gave to the AI. And then, as it's not finding anything, it's going to try like looking for some other endpoints. It's going to start to understand the application. And then there's some point in the trace where it realizes that this application is running in Microsoft Internet Information Services, and it's also using .NET. So that is really useful information because we are going to see that now, based on that, it's going to use some common file extensions and endpoints, and it's going to try to see if some of them are available in the application. It's also going to try again with some web services, but unfortunately, it's not finding anything. So now it's going to try querying some different parameters. So you can see here that it's going to create a very big list of different endpoints to try and see how the application behaves. But for how our AI is built, first, it's going to try with a small subset of payloads to avoid like overwhelming the server. This is something that is directly injected into our prompts, so we can see these kind of behaviors when analyzing traces. Then, as it's not finding anything again, it's going to start and trying to find some different services. So it's going to create a list of different ports, and it's going to try to see if there is any other service available. Also, we can see here that it's going to try to find some common subdomains that might be interacting with the application. So after all that, after testing with all the subdomains that we can see here, and fixing the Python script, we can see that it ends up with a couple ports. Nothing really interesting, but something that really is interesting for the final goal is that it finds two different subdomains, an API and an admin. So of course, it's going to try with different API endpoints, typically what we will probably test ourselves. And at some point, it finds that there is a Swagger endpoint that is returning a 331. So it's going to try again with some common Swagger endpoints until it finds that there is one interesting Swagger UI index that is returning all the documentation from the Swagger API. So based on that, it's going to try to understand what is behind this API. It's going to graph all the endpoints, and it's going to create a list of potentially interesting paths that wants to analyze further. So yeah, now it's going to try to interact with some of these endpoints. It's going to try to see how it works. But as we are actually seeing in some APIs, we are going to notice that there are some credentials and authentication behind. So the AI is also able to figure that out, and it's going to try to see and analyze if some of these endpoints are reachable without any authentication or credentials. So yeah, you can see here that some of them are not accessible. So again, it's going to try different things. It's going to try to move to back to the main application. I'm going to go through it. But at some point, it's going to find a really interesting endpoint as part of this Swagger documentation, which is the JS expression result. It seems that this endpoint might be executing some server-side code. So of course, this is something really interesting for the AI, and it's going to start testing with some payloads. So now, if we go through some of the payloads that it's going to create, we can see that it's going to get at some point some WAF blocked. So it's gonna see that maybe some of the payload, some of the parts of the payload are getting blocked. So again, it's gonna try some obfuscation techniques. It's gonna break these keywords that might be blocked by Cloudflare in this case. And we can see that after doing that, we managed to get a DNS callback, which might be a potential RC. So of course, something that we always say, and we are going to see later, we do not validate any finding unless we have a clear evidence that we managed to actually exploit something. So even though the AI is figuring out that there might be a server-side JavaScript injection, it's going to try to expand this attack testing, and it's going to try to see if there is any way to exfiltrate commands from the server. So yeah, I'm going to go through some of the traces. So at some point, you can see that it managed to create a payload, which is really interesting, using this function and the ActiveX object to execute code and exfiltrate to, in this case, our interactive stage server that we are handling on our side. So yeah, there you are. You can see, let me pause this. You can see that there is, the whoami command that is getting exfiltrated to our server. And yeah, now it's gonna make use of the proper tool that we have integrated into these kind of traces, which is going to basically replicate the same executing in this case whoami/all and exfiltrating all the command to our server. So you can see all that there.
Okay, let me share again my screen.
Okay. Yeah. So this was a really good example, and it was super cool to see. But there's a lot of things that we had to deal with during the process. So yeah, just in case someone wants to build something similar for bug bounties, you have to know that we went through a lot of different challenges regarding AI costs, some things that were proper to like typical in bug bounty, like recon, the duplication of assets, expanding the attack surface. Also, some other concerns that we have were more security related, like establishing boundaries, staying within scope, reducing the amount of false positives. On the right side of this slide, you can see a graph, which basically shows our reputation in Hackerone during the last few months. And many of the big jumps that you can see in this graph were the reflect of these improvements that we were making during the process. So anytime that we managed to solve any of these challenges, that was directly translated into better results.
Sorry, I was mute again. Okay, so now before going through all these challenges that Diego was mentioning, I want to give you a quick overview of the minimal architectural approach that we think you may need for in order to implement something like this. There are many ways of doing this. We are just proposing this as the minimal components that you may want to have there. But of course, there are hundreds of ways of doing the same thing. So apart from your agents, something that you may really want to consider is to have some sort of agent manager. We are going to see that this agent is going to play a key factor at the end in order to make sure that we are properly testing every site and we are making a good use of the resources that we have. Also, you will have to consider your LLM or maybe multiple LLMs. We are going to discuss some options regarding that later. And of course, an attack machine with all the tools that you may need in order to perform a pen test. Also, if you have been reading our blog post, you may be familiar with the word validators. Those are different components that we have built in order to make sure that we are removing all the false positives that any agent may be finding, as well as removing all the cheating attempts, which is quite common, and we are going to also go deeper into that later. And finally, some constraints rules. Whatever you're trying to run, you need to keep your agents under control. So you want to set and configure a set of rules in order to keep them in a scope and don't cause any issues to the applications you are testing. Regarding the vulnerability classes, there are many different approaches in order to do this. At least this is our approach. At the very beginning, we start hunting for all the vulnerability types that we were able to find. We keep adding more and more. However, this is going to depend on the approach you are following, right? We are going to see later that we start doing some changes in how we were running the scans. The more we learn and the more we experience different results with our scans. So if you are doing bug bounties and you want to apply this in that way, you may want to take into account the vulnerabilities that the programs you hack on accept, or also maybe you want to just focus on some subset of these vulnerabilities. So let's go into our first challenge. And whenever we are talking about AI, we need to know and understand the difference between traditional scanning and the cost involved with AI scanning. So whenever we are doing anything traditional, like running Nmap, Nuclei, or port scanning, the approach is more straightforward and, of course, cheaper. Nowadays, with tools like Axiom, it's super easy to just deploy hundreds of VPS servers that for a few hours, you run your scans, you get your results, you report, and then you repeat, right? The process is quite simple. We have been researching that for many years, and the solutions are out there. However, when we are talking about AIs, and especially with what we wanted to achieve, that was to fully to create a full autonomous pen test, it was quite a complex task, and we couldn't scan 3 million URLs, making use of queries to LLMs, making sure of removing false positives. So the process was quite more complex than going into a traditional approach. So we knew that we couldn't scan the whole internet and just pen test 3 million URLs. So we need to start looking for alternatives in order to pick the juiciest targets or the high value targets from that sea of URLs, and start optimizing as well our scan logics and start saving resources. So regarding cost, even if now using only bounty rewards in order to compensate the cost of using AIs to fully automatize this, it's not profitable. Not everything is bad here, right? We have seen during the last year that the major providers of AI models have reduced up to 100% their costs in their APIs. And this has been observed not only for OpenAPI and Anthropic, but also for Gemini. And this is a quite interesting approach. So because even though now it's not profitable to only use bug bounty rewards for this, maybe in a year will be profitable. And so our recommendation regarding this challenge is start moving on now into trying to integrate AI into your daily workflow. So in 1 year, when everything it's cheaper, you will be able to start running those tests and making some money out of them. Based on that, we needed to face a different challenge, and we needed to find those millions of URLs, right? So as any bounty hunter, we had to build our recon and asset discovery infrastructure. We did all the traditional things like expanding wildcards, finding subdomains, looking for certificates, port scanning, everything. But we also did some interesting things like using LLM in order to scan program policies. So it's quite known or typical that program owners don't usually set up properly their assets in scope on their platforms that they use. So looking at the policies is super interesting because you can also extract things like in and out of scope assets, or also in and out of scope vulnerability classes. And this is related to what we were mentioning before, right? If the program doesn't accept open redirect, maybe it's something that you want to remove from your scans. The interesting thing here is that when you usually build this in a traditional approach for bug bounties, speed is a key factor, right? You want to be the first one finding the asset, the first one finding the vulnerability, and the first one reporting it. But we didn't want to play that game. We wanted to go deeper into the applications. We wanted to start finding vulnerabilities that were post-authentication or that require more complex logical thinking than low-hanging fruit vulnerabilities. So that particular thing make the creation of this whole part much more easier. Once we collected all the URLs, we were kind of in the same stage, right? We had all these millions of URLs, but they were too many in order to be scanned with this full autonomous approach. So we needed to find out a way to reduce those numbers of URLs and to get the best or the high value targets out of them. So we came up with 2 different approaches in order to start reducing the amount of URLs we were testing. The first one was to start building some sort of target scoring. The idea is to find out from all those URLs the high value targets. And we're going to see how we approach that. And after that, the second approach we took is to perform some sort of deduplication. It's super common to see programs hosting applications hundreds of times. And when you look at those applications, they are all basically the same. So we wanted to just test only once every application and not use all resources to scanning hundreds of times the same application. So let's move into the first approach. For this case, in order to build the target scoring, here you can see some of the examples of the data that we start collecting. So the idea was the following. We wanted to visit every single site that we had in our list of targets and start collecting metadata from them. This came out of a lot of experimentation. So we start collecting more and more attributes in order to get a better understanding of those applications. And the idea was to build in this intuition that the human has whenever it's trying to pentest an application. So Personally, when I'm doing bounties, I always try to manually access to the website, go through all the assets in scope, and try to understand how likely they are to be vulnerable. For example, if I see some legacy forms, legacy extensions, or if I see that the application have some error messages, that results super interesting, and I'm probably going to focus on those targets. So the idea was to mimic that human and pen testing behavior into our platform in order to identify the most interesting targets from those URLs. Here you have a lot of examples, but some of the most important ones may be like if the application has a WAF, maybe we just want to discard that from now, or if it has some legacy API extensions, we could also prioritize those targets. So we built a wide system in order to mimic that behavior, and that will give us a single score for each URL that we have in our list. The higher the score, the more interesting the target is, the more likely to have vulnerabilities that application is. And with that, we were able to split interesting targets from the noise or not that interesting targets. And for the second, so at that moment, we still had a lot of URLs to scan. So we needed to do a second approach that was the deduplication. And the idea here was to identify all those similar targets and scan every single of them only once. So as I was mentioning, it's pretty common to find the same application hosted hundreds of times. So we start building some sort of detection in order to identify this. The first approach we had was to some sort build and identify duplicates based on the host name. Like, it's typically common to use prod, staging, or dev environments in the hostname. But at the end, this wasn't providing much results for us, so we decided to move into a more advanced approach. And in this case, we start thinking about taking and collecting 3 different attributes from every site. First, we will do some image comparison from all the URLs we had. Then we will also do a DOM HTML comparison, and finally, a text comparison. If we go a little bit deeper into the details of each of these cases, when we talk about image comparison, what we decided to do was to let the page load fully, and then after that, we will take a screenshot and create a visual hash from that screenshot. Comparing those hashes and the distance between those hashes allowed us to be able to identify how similar those images are. Obviously, helping us to discard pages that look super similar. When we talk about DOM HTML comparison, what we did was to extract all the DOM from the application, create a sim hash, and then start comparing all those hashes by counting the difference in the bytes that they have. The more different they are, the more different the HTML is. You may be wondering why we did this with the HTML, and it's super common, for example, for applications to allow you to customize your login page, right? So usually clients can go and set up their SSS configuration, changing the colors and also changing the images that you display on your login page. But the application behind that is always the same. So we wanted to discard all those cases by using this technique. And finally, we decided to do a text comparison. And here we not only compare text, but also the meaning of those words. And it was super interesting for cases like marketing websites, where you have a different marketing page depending your country. So usually they all have kind of the same menu with the same meaning, but just adapted to a different country. So with that, we were able also to discard those cases. In this case, what we did was to extract the content, the visible content from every page, create some embeddings, and then use the cosine difference in order to compare them all and identify which ones had the same text or meaning in their visual text. This approach, the target duplication, was the last push that we needed in order to reduce that millions of URLs into a much smaller number that we could potentially scan for vulnerabilities.
Okay, and now let's go to the next challenge. So for us, one of the most important things was to make sure that every asset that we were testing from this list that Joe was mentioning was tested in depth. So basically, that means checking every endpoint with every single attack type based on the context. The same as a human would do. So as we were seeing before, there is some sort of agent manager that is in charge of making decisions and start like deciding whether to test for some specific vulnerabilities or others. The main objective of this is to avoid blind scanning and to scan efficiently. And as you can see here in the graph below, here we have like at first instance a gray area, which is the discovery phase. So the agent manager is going to start running some discovery and agents that are going to start getting some different endpoints from the application, start navigating, crawling, fuzzing, reading JavaScript files, and all that. And then, depending on the context and the features that it has, it will start spawning different agents with different attack types. So that's the only way that we found in order to cover as much as possible the applications and to make sure that we were testing every single endpoint and we were not missing any vulnerability. Okay, and now another challenge that we have, and this is something that also bug bounty programs are really concerned about, are boundaries. So we know that HackerOne bug bounty programs have their own policies where they basically define which assets are in scope, what type of vulnerability they are willing to accept. So we wanted to make sure that all this information was automatically parsed by our system. And based on that, we were starting to generate some rules, both logical and DNS and at DNS level, to avoid testing up things that we don't want. A really good example of these are CDNs. So, you know, whenever you start testing an application, it could happen that some of these applications are interacting with CDNs where they probably can load some resources. So of course, we want to be able to allow this kind of loading, but we don't want our AI to go out of scope and start testing this CDN third-party provider. So that's why we started creating these boundaries and these rules to make sure that we were always in scope. Also, something really important about this is post-exploitation. So generally in bug bounty, and I say generally because there are always some exceptions, once you find a vulnerability, let's say an exploit injection, you don't need to do any post-exploitation. So as far as you are able to prove that the vulnerability exists and you provide the steps to reproduce it, you don't need to go deep and dump all the information from the database or start removing records from there. So that's why we implemented also like a policy checker that is in charge of validating this. So always the agents, whenever they want to try or execute a new command, they have this checker that is in charge to making sure that we are not doing something that is going to cause any negative impact on the applications or the users. And now we come to the next challenge, which is dealing with false positives. We know that LLMs tend to have hallucinations, and it's really hard to change the results of an LLM once it's really sure that it has found a vulnerability. So it's really hard to change the mind of an LLM. So for that reason, we wanted to make sure that we're not wasting our own time. And for that, we created a bunch of different validators that are going to allow us to make sure that what we are going to find are true positives. So a really cool and simple example is the XSS. Okay, so whenever the AI thinks that it has found an XSS, it will start using a header browser that basically will execute the request, and it will verify that the alert dialog or whatever is getting executed into the application. These kind of validators are also really useful because they were allowing us to start detecting more complex bugs like time-based SQL injection or RCs where you have to exfiltrate a command through DNS or HTTP callbacks that we were seeing in the previous example. So yeah, we had to improve a lot our prompting as well because this is also something important. And even though we were improving that and we were improving our validators, we saw that some models are really prone to cheating and they really like to bypass these kind of validations that we were creating. So now we are going to see some examples. But before that, there was a paper that Anthropic was sharing some months ago, where basically they were talking how Sonnet 3.7 was really prone to this kind of reward hacking, where instead of getting to exploit the vulnerability, or instead of going to the objective, it was finding other ways to bypass these kind of validations. And also they were talking in this paper how they improved that into Sonnet 4. And here we have some examples that we saw during our triage and our improvement of the AI. In this case, you can see that we were trying to exploit an XSS. In this case, the objective was to get an alert dialog with 666. So if you can see here, and if you count the number of slashes that we have in this URL, you can see that there is exactly 666 slashes. Yeah. That happens basically because there was some functions and JavaScript code that was trying to count the number of slashes, and it was printing that in the console log. So the model was using this condition to bypass what we were asking to, that it was printing 666. And this was abusing from this to try and bypass our validation mechanism. Of course, these kind of things are now fixed, and we are no longer getting these kind of bypasses, but it was funny to see how the validator was trying, how the models were trying to bypass our validators. If we move to the next one, we can see that in this case, again, Alvaro was super happy. There was an application which has an endpoint with a chatbot, so it was an LLM. And we saw that at some point it was trying to use the LLM chatbot to ask for a very specific command. So in this case, the M command, and it was trying to bypass the validation process by satisfying the objective in this way. So again, this is something that we have now control. But if you are planning to, like, validate and get true or false positives, you have to take all this in mind. And another example, this is super simple to understand. We have some sort of leaked secrets validation where whenever we find some secrets in the application, we will send through it and we will get if it's working, if not, and it needs a valid token in this case. So at some point we saw that the LLM was trying to generate its own fake GitHub token, and then it was sending this to our validator mechanism in order to, again, bypass the validation process. Okay, and we were saying that some models are really prone to cheating, but also some models are really good and better than others exploiting some specific issues. So what happens if we have a model that is really good exploiting cross-site scripting, while we have another one that is really good at, I don't know, crawling the application or navigating through an application using a header browser? Of course, ideally, we would like to combine both. Okay, so here's where we want to talk about the LOI models. This is something more technical in terms of AI, but our head of AI, Albert, was sharing a blog post a couple of weeks ago talking about this. Basically, the idea is that instead of using one single model, you can combine different models in order to improve the overall performance. So whenever you want to do a call to a model, instead of sending always to the same one, you will flip a coin, and depending on the result, you will send that query to one model or the other. The good thing about this is that whenever you do this kind of switching between models, you have to add the full context and the conversation history to the other model in order to understand what's happening behind the scenes and what is the full testing process that we have been following. Also, we discovered that the performance of the combinations of individual LLMs were outperforming the individual ones. So it was really good to combine those in order to get better results. And here we can see this very clear. So in this case, we were comparing Sonnet 4 versus Gemini 2.5. So basically, we saw that by combining both of them, we were improving our results in our benchmarks from 25% to 55%. So just by mixing the models.
And now I want to show you a visual example of what it looks like to combine models. So it's a super interesting approach. I wanted to show you this example. So this is a trace from a blog post we shared a few weeks ago from an RCE detailer. And I have highlighted the different models with different colors. We're going to see one model in red and one model in purple. So at the very beginning of this trace, we were using the red model, and we can see that this model has proposed a super short analysis and has directly started using Python, trying to look for the OpenAPI file, looking for more additional information about how the API works. If we move forward into the trace, we're going to see that the next call is made to a different model, the purple one. So in this case, we can see that the model is a little bit more verbose. We are seeing more content being displayed, as well as the model talking about particular vulnerabilities that could affect that particular endpoint. If we move forward, we're going to see that this particular model decided to go straight into the attacking mode and try to build a POC for that possible vulnerability, right? Instead of discovering how the application works, decided to just move directly to testing. After that, the same model is being queried, and you can see that this time the response is much more longer, proposing a lot of different techniques, attack types, or things to take into account about the application, even proposing how to exploit an XXE vulnerability. So this model is contributing a lot into the analysis process, and it really likes to, we can assume that it really likes to go into attack mode, right? So again, it's going to create a different script in Python to go and test this XXE approach and try to exploit it against the application. After that, we change model again, and we can see again that we are moving back to a shorter response with a more concise analysis. And we can also observe that this model decided to go back into discovery mode, right? Decided to go again to the open API to start understanding a little bit more about the API and see how else we could move on into attacking these targets. So this process gets repeated over and over again, and we can see how these different behaviors combine themselves, probably creating complete different situations that you will get and experience if you are just using one model. Okay. So let's go now into our last challenge. And in this case, the thing is that we were wondering how we could improve our scanning settings. And here we are talking about multiple things to improve. One thing could be the amount of steps that we allow to run to each agent, the amount of retries or the amount of agents that we launch for every target. We can even specify how many targets we can use per vulnerability or attack type. So there are many things in order to take into account when you are launching a particular scan against a target. Something that we learned about this is that more attempts doesn't mean better results. At the very beginning, we start running all our scans in a blindly, without properly, like we were performing any particular configuration at all. But once we gather enough information, we start looking through the numbers and the metrics. And Vincent, one of our team members, decided to start looking for diminished return results. So it is really common when we are using this type of agents that probably 80% of the cross-site scripting vulnerabilities are found at the first 10 steps from every agent. And then you have another 20% that you can find by letting the agent run 20 steps more. So the thing is that if you are able to find that sweet spot where you can get that 80% of the vulnerabilities without having to spend 3 times that amount of iterations, you will be able to save resources, and you could just save resources or put those resources into another type of attacks or scans. something really common is that if you're looking, for example, for leaked secrets in one application like API tokens, you don't need to spin 10 agents to go through the whole application and look for secrets. Once you have covered the whole application and you have all the responses, you can just have one agent looking for those secrets instead of having multiple agents. A different situation happens when we look, for example, for RCEs. Finding RCEs is a much more complex task, so you may need to put those resources there in order to find more of those vulnerabilities. As I mentioned at the very beginning, we start running all our attack types and keep adding more and more in order to improve the things we were doing. But once we were able to improve that, we start fine-tuning or properly configuring our scan settings in order to save more resources and even find much more amount of vulnerabilities. Actually, this was probably one of the biggest push that we saw in terms of reputation. Because we were spending much less resources than before, but we were getting even twice as vulnerabilities that we were finding before. So to do a quick recap about everything we have seen here, we have gone through all the challenges that we have been facing, all the things, all the situations that force us to improve. And the intention is that you take into account those challenges and our recommendations if you're trying to integrate and build AIs on your own. As we mentioned, at the moment, bug bounty rewards are not enough to cover, to make it this profitable. But probably in 1 year, this is going to completely change. So make sure to start working on this if you want to involve AI somehow in your daily workflow. And also make sure to take into account the things we have shared with you in order to not face the same challenge twice. Finally, we also want to recognize that this is a whole team effort, and we want to say thank you for the whole team for all this hard work they have put into our agents.